Okay. Okay. Hello, everyone. It's my pleasure and honor to introduce to you Nakul Garg, today's speaker. Nakul is a fifth-year PhD student at the University of Maryland, College Park. He is advised by Professor Nirupam Roy. He's a part of the iCosmos lab. He works on developing low-power systems optimized for resource-constrained environments, including innovations in low-power sensing, wireless communication, and embedded artificial intelligence. He's a recipient of the Anne Wiley Dissertation Fellowship, 3-Minute Thesis Award, and a lot more things, which he has not talked about. His recent research on low-power sensing for micro-robot navigation received the Mobisys 22 Best Paper Award and was selected for the ACM SIGMOBIL Research Highlights for the year 2023. So he has a lot more awards than this. This is just the tip of the iceberg. And he's previously interned at NEC Labs and Microsoft Research, which are one of the top two places in the field of mobile sensors and wireless computing, obviously robotics as well, right? The floor is all yours.
Yeah, hi everyone, and I'm really happy and excited to be here, and thanks to Nitin for inviting me to this seminar. So today I'd like to talk about on my work on wireless sensing, especially for robotics and perception applications. And before I begin, let me tell you a little bit about myself again. I'm a fifth year PhD student at UMD College Park, and I'm advised by Nirupam Roy. And in my research, I design intelligent mobile systems that spans various computational and hardware innovations, especially in wireless signal processing, embedded AI, and hardware. And my vision is to work towards reducing the hardware complexity in all types of devices. And to solve this, we are basically moving away from hardware dependent approaches to more machine intelligence based approaches. And it's all about making hardware suboptimal and dealing with its shortcomings in software using the advancements in AI and so on. So when I joined PhD, we have started working on a lot on low power sensing, and it started with making this first project on self-defense systems for drones, right? And as we started working on these topics, so I and my advisor basically stumbled upon this insight that sensors fundamentally are relying on these hardware requirements, right? And it's mostly the power consuming ADCs or high frequency oscillators, everything in the hardware front end, that is the bottleneck to making these devices ultra low power. And if we could somehow simplify these hardware requirement front end, we could create like extremely efficient and possibly self-sustainable sensors that can just rely on the harvested energy from the environment and will not require any maintenance from the user. So this inspired us to think about using different ways, different metamaterials to perform sensing, and unlike conventional sensors. So out of all these works, I'm going to share some of them with you today. I'll be talking mainly about these three works in our lab. The first one is an acoustic localization system called Owlet, and it tells how we can use 3D printed structures to tell the direction of any incoming sound. This has applications in robotic navigation, localization, and also you can put this on top of your Alexa and Google Home devices, and the Alexa can tell from which direction the user is. And based on that, it can take contextual actions accordingly. Second, we'll talk about Spider. This was a follow-up work of Owlet, and this work focuses on acoustic depth imaging. Can we tell the depth from acoustic signals, from acoustic reflections, without consuming too much power on the robot? And the last part that we'll discuss is called Sirius. This is one of the recent works that I've been doing. It's on how can we scale these ultra low power things across cities, and can we tell the location or track our assets, our packages, and our drones throughout the city without having to deal with the shortcomings of sound signals. So in this project, we explored radio signals. Can we harvest energy from the ambient radio signals and use that to localize our things? Okay. So I'll begin by talking about Owlet first. This was work published in Mobisys 2021. So The idea behind all it is that sound localization has so many applications, from health monitoring, voice assistance, uh, fine-grained robotic navigation, and various ambient sensing like human-centric and assistive technologies that are relying on localization of sound. And most of these acoustic applications require only one microphone. And this microphone basically records the variation of sound pressure in the air over time. Right? However, sound waves are a space-time phenomena that propagates in space. Right? And localization of the sound source, or finding the angle of incoming signal, requires sampling the wave at different locations in space simultaneously using more than just one microphone. Right? And localization of the sound source requires sampling this wave at different locations. And interestingly, the spatial resolution uh, depends on the size or the aperture of this microphone array. So the larger the array, the better resolution we can achieve. On the other hand, if we try to increase it too much, we start getting ambiguity. And this is the threshold, which is equal to half of the wavelength of our sound, right? So which means that for lower frequency sounds, for such as like human voice or other audible sounds, which are typically lower frequencies, spatial sensing will fundamentally require a bigger array with multiple microphones, and all these microphones have to be sampled simultaneously to be able to achieve this resolution, right? But as we see that as ubiquitous smart devices around us are getting smaller and ultra low power day by day, these large and power hungry arrays are not really a good fit for such devices. So how can we enable high resolution sensing, high resolution angle of arrival in such a resource constrained small form factor and minimal energy requirement? And this is the challenge that we solve in this work. So surprisingly, we see that sound localization in this small form factor is not rare in nature, right? We saw that common owls can actually pinpoint these low frequency signals using the asymmetric structure of their skull and this auditory system, right? We see at grasshoppers. Grasshoppers, they have body size of just a few centimeters, and they can find the direction of sound with wavelengths bigger than 10 times their body sizes, right? And it is possible because their body structure itself embeds some directional signatures, some directional cues to the incoming sound. So taking inspiration from nature, we developed an alternate design, which we call Owlet. And Owlet is a miniaturized and low power spatial sensing system. So this small device is comparable to a large 9-element microphone array, but it consumes only 100th of the energy, and it's 9 times smaller than this traditional array. Right? So in this part of the talk, I'll first look at the intuition behind Owlet. Then we'll talk about the core challenges and the system designs. And finally, I'll show you a demo along with some evaluation results. Right? So let's first talk about the core intuition behind this. So we introduce an acoustic microstructure around the microphone, and we call this structure as stencil. Right? When a sound interacts with the stencil, a directional signature is embedded to it. And the frequency response of this incoming signal varies when the direction of sound are different. So the stencil contains random holes on it, right? And when the signal comes, it diffracts upon meeting the holes, and the holes act as these virtual sound sources, right? And these virtual sound sources will then get reflected within the stencil in a constant path. And in other words, we can see that we are basically controlling the multipath, which is the various paths the sound says inside the stencil, by controlling the shape or the pattern of these holes around the stencil. So on top of controlled multipath, to achieve good enough diversity at lower frequencies, we also employ other physical phenomena like capillary tube and microresonators but I'll skip these complicated parts a bit and refer you to the paper for more details. But here's some of the stencils that we designed to increase this diversity. So now that I've talked about the fundamental concept of Owlet, let us look at the challenges, the research challenges that we face in practice when we try to implement this. Right? So consider the stencil with varying patterns for different directions, and sound waves that are coming from one angle basically creates this unique signature, the signature theta1 for this recorded signal. Now, similarly, another sound coming from another angle is creating a unique signature, signature theta2, and we basically collect these signatures from one-time calibration and later use them to estimate these angles. However, note that if the incoming signal itself has an unpredictable response, then this will also mix up in the signature and it will change the signature itself. And we can no longer use that signature as a lookup table to tell the angle, right? And due to this, our system is now dependent on the source signal, and it can only work for known transmitted signals and not for any arbitrary incoming sound, right? So this is a big challenge for us. Moreover, on its way to the stencil, the sound signal can reflect off from other surfaces like walls or furniture, right? And these multipaths, these environmental reflections can also be included in the received signal, which overlap on top of each other and are now difficult to separate in the received signature. So because of these multipaths, the system can only work in places where it is calibrated. You can't really take it to a different place, a different environment, different room, and expect it to estimate the angles, right? So we solve this in our system design by addressing these challenges. And overall, our goal is that can we design this sensing system that we train it only once in lab, and then it can work on any unseen environment and for any type of incoming sound signal. So to see how we did this, let's consider this signal modeling. So the sound signal X is first impacted, or it goes through the environmental impulse response, and then it goes through the direction-specific impulse response from the stencil. An impulse response is basically just a multiplication in the Fourier domain that occurs on this transmitted signal. We'll talk more about this. So the received signal can be written as a simple product of X, H environment, and H stencil. This is basically our received signal. So we have introduced a reference microphone and we place it right outside this stencil. When the same sound is received by this reference microphone, it will not only be affected by an environmental impulse response, and Y out will be equal to the product of X and a little different H prime environment, right? And now we see that the source signal X can be eliminated by simply dividing these two signals, right? Which means that Y in divided by Y out will leave out the ratio of these environmental impulse response and get rid of X. And this ratio is basically the impulse response, which is a combination of the stencil and all the environment effects combined in one, right? So aim is that can we learn this S stencil part through our one-time in-lab calibration, which is done probably during the manufacturing process of the stencil. But these ratios of these environmental response is still dependent on the external environment, right? So if we take a closer look at this, what basically is happening is when these two microphones are placed at an arbitrarily different location, they of course have arbitrarily different environmental responses. On the extreme end, if somehow we superimpose these microphones, place them at the same exact location, they will have exactly equal environmental perspective. But we are somewhere in the middle. We cannot virtually place them on top of each other, but we can't really separate them out also, right? So we place them so close to each other within a few millimeters that the highest wavelength of our incoming sound is beyond the ratio of these impulse responses. It's basically bounded within this limit, And we take advantage of this bounded distributions and we try to learn it in our calibration step itself, right? So to do this, we basically create a synthetic data set by emulating different environments and learning this distribution of these ratios for all the environments. And then we train a neural network on the frequency and the phase spectrums individually for these signals. So once trained, it can work in any arbitrary environment and estimate this angle of arrival in real time, right? So let's talk about some of the evaluations, and I'll also show you a demo for this. So to evaluate this, we basically compare Owlet with the traditional arrays that people use, and we create a setup of 9-element microphones and evaluate in terms of the energy consumption, the accuracy of angle of arrival, and localization capabilities. Right? So in this first figure, I'll show you the accuracy and the energy trade-off for compared to traditional arrays. Here, the X dimension is showing the median error, and the Y dimension is showing the energy consumed in millijoules. And the more we move towards Y-axis, the more energy is consumed by a system. So naturally, the closer to the bottom left of the figure, the better the system is, right? It's consuming less energy, it has less median error, it's basically performing in idle case, right? So as we can see, the traditional arrays with less microphones consume less power, but the direction of arrival accuracy is not very accurate, right? So as we add more microphones from 2, 4, 6, 8, and as we go to 9, this accuracy is increasing significantly. But notice that this y-axis is in log scale, right? So with that increment, with that improvement in accuracy, we have this huge cost of energy that is being consumed. So on the other hand, if we look at Owlet, it basically performs in both these dimensions, right? It's consuming only 16 millijoules of energy, which is way less than even the 2-microphone array system. And it still has a 3.6 degrees accuracy, which is comparable to the 9-microphone array, right? And this is all due to the diversity of the stencil. So you may ask that why is Owlet's power consumption lower than the 2-microphone array if both of them are exactly 2 mics, right? And this is because we do not just optimize our stencil design, but also our machine learning algorithm, which saves energy compared to the traditional Fourier transform and music algorithm, which is used in these techniques, right? So here I have broken down the energy consumption for different modules of our system. As you can see, Owlet consumes same energy for the hardware front end, which is the microphones and amplifier and hardware energy. But because of the software optimization itself, the compute energy is much less. And note that over here, y-axis is in log scale, so it's not really half, it's almost 10 times less than the 2-microphone array, right? Uh, we show the CDF of the median errors, which basically shows that how Owlet compares to these array-based algorithms in terms of compute. And we compare the spatial spectrums. Here you see on the right-hand side, Owlet has a much narrower resolution compared to the state-of-the-art, which only relies on arrays. So we have evaluated it in different environments, including indoor labs, lobbies, and outdoor open spaces. And we trained it only once in the lab itself, and then testing it in different environments tells us that basically the system works equally well in unknown and unseen environments, right? So we made a localization system and put it on top of a moving robot. And we had 2 speakers in the lab, and we tried to localize this by estimating the 2 angle of arrivals. And then we see that we can effectively localize a robot within 10 centimeters of median error. And naturally, if you see the error starts to increase, the farther you go from the speakers, because the same angle deviation leads to a larger localization error, right? So we have more evaluations that I'll skip for the interest of time, but please feel free to look at the paper for this. But I would rather show you some demonstration for how this works.
In this demonstration setup, we have our stencil attached to a microphone. We have placed a speaker in front and it is powered by a signal generator constantly transmitting sound signals. The speaker is mounted on a moving platform and its location is being estimated and displayed on the screen in real time. This is a raw output from Owlet without any post-signal processing. And as we can see, the location is within a few centimeters from the ground truth.
So in this, we saw the first intuitions of how can we use these 3D microstructures and then tell the angle of arrival of any sound signal, right? And this demonstration helped us get some awards at Mobisys, and it was the cover story of the Get Mobile magazine. And you can learn more about this project later. But as we saw the first intuitions, we started thinking about, okay, we can do localization angle of arrival, but what about some more complicated tasks? Can we like image our surroundings using this? Can we tell the depth, just like we have Microsoft Kinect and different LiDARs? Can we replace those power hungry things with some low power 3D printed structures? And that's where the second work comes in. And for this work, especially, we dive deeper into autonomous robots because they are the ones which are making so much noise. And we see that, can we solve autonomous navigation, and can we help these tiny robots to understand their surroundings better using these things, right? So we looked at various applications where this can be applicable. We can probably revolutionize the way we do farming. We can have precision farming and agriculture using these robots, right? We can take them for disaster management and search and rescue operations, and they could be the first responders that can help us uh, rescue things. And they have many more applications that are beyond that can take so much time, right? So to apply these tiny robots in real world, we still have to solve these core challenges, right? So in this work, we focus on the perception part of it, right? So interestingly, we have all seen that navigation problem in autonomous cars, right? And how they solve this. They already navigate on busy roads. And unfortunately, these techniques cannot be applied on our tiny robots because they are just too power hungry, right? And LiDAR, which is the most prominent solution, it itself consumes tens of watts of power to create these 3D maps of the region. Like radar requires multiple watts of level because it has these power hungry arrays like we discussed that it used to beamform and scan it one by one, right? And this sets this fundamental limit on the smallest size. And even depth camera consumes multiple watts of power, right? So while automatic driver cars and self-driving cars, we can put on these huge power supplies to power them up. But in our case, we are targeting these small robotic cases, which only have a few milliamps of battery available, right? So if we look at the power distribution, the breakdown of a typical robot, we see that uh, the most power hungry part is the actuator, right? They consume almost 60% of the power, right? And within the remaining power, apart from actuation, these tiny robots have just 10 to 30 milliwatts of budget for sensing plus the computation and other things. So if we go over these existing navigation solutions, they are just too power hungry to be applied on this. So we asked this question that we challenged ourselves in asking, can we enable navigation on these super low power robots that fit only in a few inches, right? So the answer is, of course, yes. And our system only consumes 10 milliwatts of power with one pair of speaker and microphone. And before I tell you the intuition, let me explain where the core challenges for these applications are. So these navigation sensors basically try to produce this cross-sectional depth map of the scene so that it can identify the location of nearby objects or basically obstacles for the robot. So if we rethink about this navigation problem, basically what these navigation sensors are doing is they are searching each directions and looking for some reflected signals, right? Existing sensors scan the scene only one angle at a time, right? So there are two kinds of scanning. One is this mechanical scanning, right? Where we put a motor and it keeps on rotating. And the power consumption for these mechanical scanning is too high. So it requires a motor and everything. Another kind is called beamform, where we emulate scanning an array of speakers or array of transmitters. And this does not require a motor, but it can still do very fine and fine range scanning with less than a degree of resolution. Right? But this architecture will require so many transceivers which are parallelly synchronized with one single processor, which again leads to a higher power. Right? So, okay, scanning will fundamentally is a power barrier. So in our approach, we meet this low power, small size, lightweight requirement, and we want to break away from these scanning based navigation ideas. And next, I'll introduce how our core intuition is. How do we approach this thing by something known as coded signal projection? Right. So we envision a concept, coded signal projection. And let's first review what this signal propagates, it processes in the real world. So when a signal is transmitted, it propagates everywhere in the environment, right? And here, what we plan to do is we want to transmit some directional coded signals that are completely different, dependent on where each direction they go in, right? They have different patterns in all these directions. So if a reflection comes back from an object, we would fundamentally know that if it's this unique signal, it must come from 45 degrees because that is the only angle we transmitted this unique signal at the first place, right? And if we can tell this unique signals, even if they are added up and received by the same microphone, we can unravel these reflections based on the orthogonal properties of these signals and find out which exact directions they are coming from, right? Of course, depending on the texture of the object, the size of the object, the power will vary of the received signals. But as long as we design distinct enough or diverse enough signals, we could separate them out using computational techniques. Right? So again, how the sensor array does it is by using phase delay, and that is how they generate coded signal projections. But in our case, we are avoiding this and we rather go with these 3D printed acoustic structures, again, calling them stencils, that will help us emulate these sound sources. So here I'm showing this internal view of a stencil, and it has many parts inside with different lengths. One is longer with the curvy wave, and another one is the shortest path that can go outside. And these tubes basically are adding these different paths, and because sounds travel at a specific speed, a different delay will occur or a different phase will occur when the signal reaches on the other output side of this tube. And in this way, we are basically emulating a speaker array with using just one speaker, where we could control all these delay lines by changing the path lengths of these structures, right? So after the signal propagates through these different paths, we create a controlled multipath that is formed in this scene. And with the multipath, the received signal at each pixel on the right-hand side, this is our object plane which we are trying to image, they are unique, right? And more importantly, since the structure is stable, the multipath is also static. It's not changing anyway. So we basically calibrate this and we once in lab and try to see what is the received signal we get for each pixel or each object placed in that pixel. Right? So this is an example of the 3D model of the stencil that we made. And of course, we need a complex internal structure that can introduce good enough diversity for each location in the scene. And we do this complicated thing by introducing helical structures, because helical shapes have this interesting property of less attenuation of the signal as it propagates and still giving us enough delay to travel through the pipe while taking less volume of the stencil, right? And this is the core intuition that helps us reduce the power consumption while using only the single microphone and a single speaker. Okay? So here we are showing a simulation experiment that we did, which basically shows how the sound wave looks once it is transmitted in a regular speaker versus a speaker with our stencil on top of it. And I want you to notice here that how each signal looks different for different angles. On the left-hand side, we have this big wavefront, this C-shaped wavefront, which is just going and it's uniform in all angles. But because of the stencil, we see all these fluctuations in the amplitude. And this is just the amplitude spectrum. If we look at other phase spectrums, it's even more complicated, right? We see all these diversities occurring because of the interference of all these waves that are coming out of the stencil. And this diversity in the output is the core idea that helps us image the output object plane, right? I'll quickly skim over the mathematical model of this, but I think in interest of time, I'll skim over how this thing works. So you can imagine that we have a matrix which captures the effect of our stencil, right? And each column of this matrix is representing one pixel of the scene. So on the left-hand side, we have this Y received signal, and on the right-hand side, we have a channel matrix, H, and our scene. Our scene is represented by binary values, which tells if there is an object or not. And our whole optimization process is to find X given the inverse of this H matrix and Y received signals. And I think we all know how we can use multiple optimization techniques and compressive sensing to solve these kind of problems. So we do some more optimization to reduce our power consumption. Instead of using our big matrix H, we try to decompose it into smaller meta matrices, and then we try to estimate those smaller regions of object planes to reduce our overall global search. This is similar to finding local minimas and not going for the global minima at the first place. Right? And this is the consumed energy with the increasing number of columns in H. And this basically tells us that if you could really decrease the number of columns in your matrix, you can reduce the power consumption of your matrix. Right? And this figure shows us the resolution that we achieve, which is within 1 centimeter of resolution. Okay, I'll go through some. We also do other optimization techniques, like we basically stack multiple images as the scene progresses, as the robot moves, and that helps us refine the final image just by stacking. And you can apply very simple techniques like median stacking, and that helps us clarify the resolution a lot. So I'll go to some of our evaluation results. This is a similar graph where we compare the accuracy and the energy. And again, the y-axis in log scale, and we are basically comparing 3 different modalities here. The first one is the very basic a distance sensor. It's basically a ping sensor that constantly looks for the distances from a space, and we put this on top of a servo motor and include this in the power budget. We compare it with LiDAR, which in this case was an Intel RealSense LiDAR, and we see that while the distance servo sensor has less accuracy, it still consumes a lot of power. But Spider is not as good as LiDAR. It has around 90% accuracy, but it has almost 100 times less power, 400 times less power compared to these two techniques, right? So if I show you some of the imaging results that we got, we basically 3D printed these obstacles. We made it like a maze, and we're trying to image it from the front side. And you see the blobs where we could see these objects present in the environment, right? So we tried it for different distances. The object, we place it farther. So the maximum range we have over here is around 12 to 15 centimeters. After that, the signal strength really starts to decrease. And these are the raw outputs, and we show the comparison of how motion stacking and frequency stacking can help us increase these resolutions over time, because the raw signal is very noisy, but we know that since most of this noise is Gaussian, we can simply stack them up and get better results, right? And here we are trying to image some real world cases. So I've just placed a book and box, and we're trying to see the heat map of can we locate these objects in space. So this is the breakdown of the energy consumption of different submodules of our system. And on the left, we are showing this prototype that we made On the top, you see our stencil with the microphone in the center of it, right? And this is a time versus power graph. And here we see that whenever we try to image, we basically turn on the sampling, the ADC of the receiver, and that pumps up the power at some certain point. After that, we turn off the sampling and we start our compute, and that is the compute part which takes much lesser power and gives us the image output. So to summarize, we introduced the usage of acoustic microstructure, but this time we did it for scene reconstruction on miniaturized spatial sensing applications, right? And this is the work which gave us a Best Paper Award at Mobisys, and it was one of the SIGMOBIL research highlights of the year 2023. So before I go to the next one, if you have any questions, I can take them right now, or we can take them at the end. So you can interrupt me right now if you want.
I had a question about when we so when in for Owlet, when we model the environment into the into the equation, then we assume that the mapping or the relationship between the received signal and the disturbances caused by the environment and the stencil are both linear in nature, because we just multiply it with H environment. And the same thing like for spider, when we do the pixel wise thing, the mapping is linear with the originally mapped signal. So I don't know the theory on this, but like how accurate is it, or is it like what is the basis or evidence of like using a linear map?
Yeah, that's a great question. So in wireless communication, wireless sensing, right? All the signals that we use, we have this concept of linear time invariant signals, right? So what it basically says that all the wireless signals on the received end can be just a summation of its own copies. What it basically means that if you transmit a signal at one place, it will come at the receiver, but will also travel and reflect off other places. But the received signal will always be just a summation of all these reflected copies. And this creates this strong linear model of our system we basically use to model. And this is what we call the impulse response, that if you transmit an impulse in space, then it will reach the receiver after certain delays, and that captures the impulse response. In vision, a lot of people like to call it the point spread function, if you have heard of it. So
Yeah.
impulse response is nothing but the point spread function with the assumptions of linearity, the linear time invariance process, the physical process of these waves, because they're traveling in space and time. There are some nonlinear properties which occur at the receiver due to the use of amplifiers and other nonlinear devices, but our microphones that we are all using are assuming this linear property. So that really helps us solving this model.
So is it safe to say that for sound, if the number of reflections or the number of objects in the scene increases, the assumption of a linear model becomes less valid?
It stays as long as, even if there are like millions of reflections coming up, and if
Oh,
even if we assume that there's no attenuation, the received signal will still be a linear summation of all the reflected signals, right? So
yeah.
any nonlinear property that occurs will not happen due to any multipath effect. It will only happen due to our transmitter or receiver's non-ideal nature. And I think we have somehow mastered this art of making good microphones that capture the perfect frequency and they transmit the perfect frequency without any nonlinear distortion.
Okay. Yeah, that was helpful. Thank you. Uh, another. Oh, let Manoj go first.
Okay. Yeah.
Hey, can you hear me?
Yeah, we can hear you.
Sure. I have a couple of quick questions at this stage. So, like about the power consumption, right? You had mentioned 10 milliwatt for one speaker and one microphone setup. Suppose we want to do this for a larger range, like 1 to 10 meter. In that case, how does power scale up?
Yeah, the power scales up exponentially because as you try to transmit more power, you need larger speakers, right? So once you go for larger speakers, you need to pump up more energy to reach that distance because the attenuation that happens follows the inverse R square law, right? So it exponentially decreases with the distance. So to cover that much range, we need that much more power to transmit. So that's one of the biggest challenges that we also really look forward to, that how can we keep on increasing the range, either by using better structures that occur less attenuation as the signal goes from the speaker through the structure, or by using better speakers that can help. Another thing people look into is reducing the field of view, because if you limit your field of view, you can focus all your energy into a limited space that can help you cover more range. So there are multiple ways we can do that.
That makes a lot of sense, Nakul. One more question. So, if you are operating in a noisy environment, right? Even in a room, you have sound coming from your PCs, people talking, walking around. So, do these have an effect on the system?
Yeah, definitely. That's a great point, because we are operating in the sound regime and all these things are noises for us, right? So in the case of Owlet, right, what we are basically operating in the audible frequency regime. Whereas in Spider, we are working in the ultrasound regime, which is above 20, above 40 kilohertz rate, right? And when we are working in these higher frequencies, there's almost negligible noise in those frequency range, unless there are like equipments and machineries which are producing these sounds. Humans do not really produce these sounds, so the noise floor is much less, right? But if we want to like design application specific for Spider or Owlet, we can first understand what are the frequency bands in which noise is mostly focused on, and then we can simply have like filters to remove those part of the regime, and also optimize our stencils to operate on a particular frequency parts. Right. For example, I was having this discussion with Nitin that if we put things on drones, and drones produce a lot of sound, right? While they're flying, the propellers are making sounds, but we did this quick experiment and we saw that all the energy that propellers produce is focused in some harmonics of these frequencies. They are like 10, 12, 14, 16. So these are all harmonics of some. And since most of the energy is focused here, we can simply filter out these narrow frequencies, and then our entire signal comes out as clean.
Makes sense. So, and when you go for higher frequencies like ultrasound, do the same microphones work, or do you get some special kind of microphone?
Right. We have these piezo-based microphones for higher frequencies that are much more optimized for those frequencies. If we can also go for megahertz, and that's but as we go higher frequencies, we will see that our microphones itself will also start consuming more power. Right? So it's a sweet spot where we find that 40 to 80 kilohertz is probably a range where microphones are good. If we go to megahertz, we'll need more sophisticated microphones, and so on.
That's all I had, Nakul. Thank you.
I think we have 2 more questions.
All right, can you hear me?
Yeah, hi, I can hear.
Hi, I have one question. So you mentioned that those are designed for a mobile robot, right? So does this method need to be calibrated if the mobile robot like moving in a high speed, for example, mounting on a quadcopter, and need to consider, for example, about the Doppler effect? Thank you.
Right. Yeah, that's a great point. So both the structure of the robot and the Doppler effect will distort our incoming signal, right? So we have to overcome both of them. So one way is after you put it on the robot, we can calibrate it for that case, but it's not required as long as the robot is not blocking more than 20% of the scene, right? If it's blocking a lot of the scene and you still want to see through that thing, then we need calibration. But if you are fine with it, we don't necessarily need it. And Doppler is frankly easier to solve in this case, because most of these robots will have IMUs that can tell you the ballpark speed of the signal, right? So if you know the speed at which you are moving, if you know the frequency that we are transmitting, we could really offset the Doppler, right? We will exactly know what is the shift to expect when we are moving at a certain speed in the reflected signal. So that part is fairly easier to solve in these cases.
Okay, thank you.
Yeah, I think Aniket has his hand raised.
Yeah, I have a very fundamental question. So how much does the material of the stencil matter in your analysis? And is it modeled into that environment factor that you considered with and without the stencil?
Right, excellent question. I think the material matters a lot because it determines the amount of attenuation that will happen in each path length, right? Because the material's texture will prevent sound to go through it, right? The other thing is not just holes, but also the structure itself. The sound will try to go through the structure, right? So how good is the structure's reflection and absorption properties? Because the signals are not only exiting the holes, they're also exiting through the structure. So we need to find materials which have good reflections but also smooth texture to let the sound go through the holes, right? So in this case, we found that resin is a very good material for this. It's 3D printable using UV. It has smooth textures which can let sound go through, and it has good reflection properties as well. So we found that this is a good one to go through. Yeah.
Thank you.
I think we should keep the questions at the end.
Okay, we'll
so
take.
that we can get through the.
Yes.
chat.
How much time do I have, Nitin?
You can keep going. It's okay.
All
Maybe I
right.
can-
All right.
yeah.
All right. So yeah, please let me know whenever I have like less time left. So I'll last part I want to talk about is that we did all these acoustic works and 3D printed works, but one day we just wondered that to really scale things on a city level, right? We have to go beyond sound, and we have to somehow bring in RF that has this great property of traveling through miles and kilometers to distances. And that's when we started looking at, can we make ultra low power GPS like system that can help we track our assets, right? So we start about thinking things at scale, and I'll not overemphasize that while low power IoT has great applications in precision farming, wildlife monitoring, climate sensing. So you can imagine like throwing these sensors in a forest that can constantly monitor the temperature and know if there is a forest fire that's happening. It can trigger the exact location at which it found the temperature. So you need to find locations of these low power sensors at scale without having to worry about maintenance, right? So we had some numbers that by 2030, we'll have 30 billion IoT devices, and why localization is important for them, right? And there's a slight difference in the earlier localization works and this work, which is the self-localization. And the point is that to truly scale a system, we require self-localization, where the sensor itself can tell its location without having to communicate back to any anchor or any offload any compute to the cloud or any other server. It's the sensor itself which is trying to tell its location, and that's where it gets challenging because the sensor is now resource constrained. It does not have enough power and enough compute to do this, right? So there are two types of self-localization systems. One is a distance-based or ranging-based systems, and another is an angle-based system, right? So both of them have limitations in power requirements. They require time synchronization between the transmitters, and in the angle-based, as we saw, that they often require arrays and sophisticated anchors, right? So self-localization is where we thought that it's still an open problem, and can we find it was a very active area of research, but low power self-localization is an interesting niche that I think we could solve, right? So before I go to the solution, let's quickly discuss this breakdown of an array-based RF technique that is trying to find the angle of arrival. So of course, they require a large number of antennas which are placed to capture the RF signal. They have these power-hungry ADCs, oscillators, and IQD modulators. And finally, they have this processor, which is running Fourier transforms and music algorithms. Right? And unfortunately, these requirements are posing the challenge for our power consumption and compute complexity. So we wonder that can we extract this AOA, angle of arrival, using just one antenna and also somehow throw away these power-hungry front-end hardware, right? So coming back to this question, antenna is, if we look at an antenna, what is an antenna? It's nothing but just a piece of metal that is capturing radio frequency signals, right? And interestingly, the shape of the antenna impacts the gain pattern of the antenna, right? The amplitude across different angles. And typically off-the-shelf antennas have this fixed gain patterns that we show here in the bottom. So we thought that what happens if we can change the shape of this gain pattern over time, right? In that case, one signal coming from one side versus other signal coming from other side can be distinguished by looking at the amplitude of the received signal. But changing the gain pattern in time is not something usual. We have not seen our antennas just dynamically change into something else like a transformer, right? So one possibility is to mechanically change the gain pattern by putting it on top of a motor. But of course, that will consume more power. So instead, we do this clever technique of using switches on top of our antennas, right? So these switches can basically connect and disconnect parts of this metal on the antenna that can potentially change the shape of this gain pattern itself, right? So it's behaving as if the total area or the shape of the metal has changed. And because we have control over these switches, it's basically like a knob that we can turn on and off programmatically, of course, and that can change the shape of the gain patterns altogether. And what happens is that we see that using just two switches, we can produce 4 different gain patterns, which is 2 to the power 2. And this is one of the first set of results that we got using our antenna that we made. And we simply collected the signal from all the different directions while switching the gain patterns. And here we see that how all the 4 gain patterns are on top of each other. And for each incoming angle, these pattern or the ratio of all these 4 gains are distinct, right? And how distinct are they? Can we check this diversity of the gain pattern? And this is the autocorrelation matrix of all these n gain patterns. And we see that as we increase n, which is the number of gain patterns, we start to see more and more autocorrelation, higher autocorrelation for only the diagonal values, which is the ground truths. Right? So for n equals to 1, which is the conventional omnidirectional antenna that people use, we have almost like no diversity. We can't distinguish signals from any angles, but as you increase, we can start seeing that diversity kick in. Right? So put it together, let's see how we design our system, and we call it Sirius. Sirius is a star in the North Hemisphere, which basically twinkles and is the brightest star after the sun. So we named it after that star. And the idea is that Sirius, the star, twinkles and it appears to change color. So we think that our antennas are basically changing beam patterns. And in the frequency domain, it's similar to like changing colors. So it's behaving as if it's a star that sailors use to localize. So we can call our antenna Sirius, which can help things localize themselves. So just a fun fact. Okay. So we first replace our large antenna array with this single reconfigurable antenna. And then since we don't need phase at this point, we are only looking at amplitudes, we can get rid of all the power hungry hardware and put 0 power consuming passive envelope detectors. They do not require any energy to operate, right? And finally, we use a very small AI model to estimate the angle of arrival by looking at these gain pattern fluctuations, right? So what's happening is that similar to our previous work, we call it directional code embedding. And as this incoming signal comes in, due to the fast switching of this antenna gain pattern, we add an angle-dependent signature to the incoming signal. Notice how this amplitude of the incoming signal is changing for all the 4 switched gain patterns. Right? And the envelope detector, the passive envelope detector, what it basically does is it extracts the energy of these fluctuations by removing all the AC component and giving us a DC equivalent. It's also known as a rectifier in for those who have done ECE based studies. It's basically a rectifier that tells you the energy or the DC of each packet of the signal, right? And this approach is what we are calling the directional code embedding. And I can go a little bit more deeper to really see how this is working on a deeper level. Right? So if we denote our incoming signal as xt arriving at an antenna, and let's say our gain pattern is a function of angle now, which is g phi, right? So we can write a received signal as a simple dot product of g phi and xt, right? And what we are doing is by changing our gain patterns, we are collecting the same signals with multiple gain values, and then we obtain this vector of y on the left hand side, which are varying for different gain patterns, and they represent the different gain values, which are the g times xt. And however, this vector alone cannot serve as the code, since here also it is depending on the incoming signal strength. But one very simple observation you see is that if you normalize it with the first row of the matrix, we can get rid of all the x, right? And now our subsequent matrix becomes a ratio of each gain value subtracted by the first gain value, right? And now this we can use to estimate our angles using our model, right? For the interest of time, I'll skip over some of them. But the core idea over here was to, if you have multiple beacons in a space, you can find angles to both of them and localize your node. But the challenge is that how do we know the signal which is coming from the 2 beacons? How can we differentiate them at the first place? So the core idea here was the beacons, we don't need to synchronize these beacons. They don't need to transmit one after another. Rather, they can transmit and at some unequal duty cycle. Okay. And then we develop an algorithm which we call the beacon identification algorithm that can tell you by looking at the received signal that which part of the signal corresponds to which beacon. And then by looking at the angle of each beacon, it can then localize. Right? But the core research challenge is how can you distinguish or decompose these two signals and label them as beacon 1 and beacon 2 respectively, right? So I'll jump to one of the core idea over here, which comes back to one of the great questions that someone asked here about linearity and non-linearity, right? So here we actually introduce non-linearity or signals for our advantage. And what we do is that if the 2 beacons are transmitting 2 signals which are of different frequencies, it will look something like this. So this is an incoming signal, but the 2 beacons have a slightly different frequencies, due to which when they overlap, they have this constructive interference where the amplitude increases. And in some parts, they have proper destructive interference. That means the received signal will be just cancelled out when both of them come. And due to this nonlinear nature of the envelope detector, what happens is your receiver has a varying amplitude of the total energy of the signal, right? So the parts where which the 2 signals are destructively interfering, our envelope shrinks to 0. And the parts where they constructively interfere, the envelope has a very high amplitude, right? And this creates a nonlinear received signal that can help us distinguish if the incoming signal has 2 beacons or just 1 beacon arriving at any point of time. And this is how one of the received signal looks like. On the top, we show that the parts where the signal oscillates, that is the region when both the beacons are transmitting. The rest of the region in that x-axis are the regions where only one beacon is transmitted. And if we know the collision windows, if we know the windows where only one of the beacon is transmitting, we could segment them out and label them as beacon 1 and beacon 2. And just by doing some very basic first derivative and energy thresholding, we can perform these beacon identification. So we did a comprehensive evaluation for this antenna. We fabricated it in-house in the lab itself. And we've made it to work on ISM bands, which are these free-to-use bands such as Wi-Fi and Bluetooth. So our antenna works in that regime. And we designed various antennas for various different sizes, starting from just 25 millimeters to large 66 millimeter antennas for different frequencies. And the right-hand side shows a ultra low power thing, which is powered by a small LiPo battery. And this LiPo battery lasts for years for a localization rate of 5 Hertz. Right? So you can keep getting your location, and still it will be so low power that this battery will last for years. And all this is due to the passive envelope detector that we use that does not consume any energy. All the energy that is consumed is either by switching off the diodes that we had on the antenna, or it's due to the processing that we do on our microcontroller. That's it. Okay. So of course, let's look at the accuracy of our angle of arrival estimation first. So this is a ground truth versus estimated angle plot where we see that we have a ground truth, which is the linear line, and the estimates are bounded within an error bar of around 7 to 8 degrees, right? So this shows us this confidence that we can get angle of arrival less than 10 degrees of error, and that can help us localize it. So we did these evaluations in UMD. So this is one of the baseball field. You see the scale by looking at the cars in the map in the second figure. And this is an experiment where we put on some anchors in the field and let our system roam around on a cart. And we try to localize that cart on all the areas in the field. And the third plot shows us the CDF of the error, right? So all our errors, localization errors, are less than 2.5 meters, which is similar to GPS. And if some applications require only 1D localization, they can get less than 1.3 meters of error, right? So we were also wondering that while we made Sirius for outdoor applications, how well will it perform in indoor applications, right? So we did evaluate for different type of scenarios where people are moving around, there's crowd, there's lab, lobby, and we see that with increasing number of crowd around the antenna, it does affect the accuracy, but it's still within the permissible limit of 20 degrees, and it can give a sub-meter accuracy for indoor evaluations. Right? So I'll skip over this. Yeah, and so this evaluation shows that how well does Sirius perform in non-line of sight cases, the cases where the signal is so attenuated because they were objects or walls between the transmitter and the receiver. So here we see that in non-line of sight cases, more than 80% of the power is gone because of the attenuation. So in that case, our median error rises above 40 degrees, which is not good for localization errors. And we design an optimization strategy to understand when a signal is in line of sight and non-line of sight, and that can help us make it resilient by not spitting out garbage values and instead take informed decisions on when giving it a confidence score on how well it is confident about the estimated value. Right? So this evaluation basically highlights this resilience property in the indoor scenarios. So again, to summarize, Sirius is our low power self-localization system that we invented to operate only on a single antenna, a single reconfigurable antenna. And to learn more about Sirius, you can look at our open source codes and all hardware designs for this paper. And we have the Gerber files also open source in case someone is interested in printing their own antenna. And that pretty much wraps my research here. And I'm again open to take questions if you have.
Yeah, feel free to raise your hand or you can type it in and I can read out the question for Nakul. Either way works. Yeah, Shaurya, you want to go first?
Yeah. So my first question would be about like in all of your works, how does wavelength or the frequency of the signal matter, and like how much does your accuracy depend on the choice of frequency band? Like, for
Right.
example, for Owlet, like you used audible range, but you switched to ultrasound for Spider,
Yeah.
and here, yeah, just
Yeah. So yeah, that's a great point. So the general rule of thumb is that higher frequencies give higher resolution, but they undergo more attenuation, so you get less range. So in Owlet, it was a more application-centric approach where we wanted to solve spatial sensing for speech, for audible regions, and that's where we picked up the challenge of can we get direction of arrival for the audible region. If we go in ultrasound, Owlet will naturally have a much better performance with shorter wavelengths, higher frequencies, we'll get a much more diverse output. But it will come at a cost of lower range. And that's what we see in Sirius. Spider, right? We went for ultrasound and our range limits itself to uh, some decimeters, right? So that is the trade-off we have to see. But at the same time, we get much better resolution to distinguish between obstacles in the environment, which is just centimeters apart, right? So this is a general rule of thumb both in acoustics and RF. For high resolution, you typically want to go to higher frequency regime, shorter wavelengths, but it will come at a cost of this lower range. So in Sirius, we found that the 900 megahertz, which is often used by LTE services, right? These are the signals which can go very long distances. With the incoming of 5G, which is the millimeter wave, new things, new cell stations are coming in. They can give you so much high data rates, such high resolutions, but they are limited to very short range line of sight, and that's why they are more focused in city level. So both in acoustics RF, this is an ongoing trade-off between the frequencies and range.
okay. Thank you for that. But like for in Sirius, like is there some uh, compromise on performance? Like does for example, if we take two things which are at the same distance, like which are the same distance apart, but we use higher frequency bands for in one case and we use lower frequency band in the other case, so would Sirius be as accurate for both of them, or like
Right,
how?
right, right. So yeah, basically in Sirius things are a little bit different. So what happens is the accuracy will be exact same for both lower frequencies and higher frequencies as long as this let's go back to the slide for this. So as long as this gain pattern remains the same, because our things are agnostic to the frequency. As long as we are able to produce diverse gain pattern, we can achieve the same accuracy. Now, the catch here is to produce these diverse gain patterns in a small restricted size of antenna, it's harder to make them diverse for lower frequencies,
Yeah.
right? So the same thing manifests itself in a different challenge where to make a diverse enough gain pattern, you need a larger antenna to produce enough diversity in that frequency. So that is why if we go to like extremely high frequencies, the millimeter wave, 60 gigahertz radios, that is where we can shrink our antenna size to almost less than a millimeter also. And that is where we can produce enough diversity. So we can still achieve the same accuracy, but the answer is it will require some trade-off with the antenna size in that case.
Okay, thank you. And just a quick question about Spider. When you do motion stacking, uh, how is the setup moving? Like how is the speaker moving, and how do you get the ground truth position of the speaker?
Right. So here we use the position encoders to understand how much did the robot move ahead. We know exactly in the terms of distance, and that helps us offset the image and then add it onto the previous one.
Okay, thank you.
Oliver, you want to go next?
Sure. Thank you, Nakul, for the amazing talk. So I have a question about, so all the tests you have done for acoustic localization and depth imaging, you operated with, like, the transmission medium is air. How would it operate with a different, like, medium? If, so, for example, if you are underwater, how would that affect your design?
Yeah, thank you for bringing it out. That's a great point. So we are actively working on taking Spider to underwater, right? Because that's where its application really helps us. Because in underwater we can't use RF, right? And even visible light is not a good way to look at things underwater. So that's where sound can really help us look for coral reefs and map the underwater, the deep sea beds. So the only difference in the term of technical changes is the speed of sound, right? So the sound, the same frequencies will have different wavelengths, and that will require a different optimization of the stencil that is optimized to produce diversity in those wavelengths, right? Another technical challenge in underwater is a different multipath profile. So unlike air, where sound travels in a straight line, in underwater, due to the temperature changes and the density changes, the speed of the sound is not constant. The speed of the sound changes with the depth. So we need to overcome those challenges. Another challenge is um, in case of shallow water, the sound is getting reflected not just from the deep sea, but also from the top where the air and water boundaries there. So that adds in more and more reflections coming from the environment. So it's a very harsh and noisy environment to operate in, and that requires more innovations to take it. And we can't just simply optimize something in air and put it in water directly. But that's an active area that we and other people are also working in.
Yep. Thank you so much. Thank you.
Great. So I have a couple of questions before other people are thinking about it. So the first one is you showed a plot of the array versus the 9 microphone array versus your owlet, like way back in the slides. And obviously the accuracies are comparable, but I also noticed that owlet was slightly more accurate. Do you have any reasons as to why you think that was? That's the first question. And the second question was, do you think adding passive structures to an array of microphones would make it better?
Right. Yeah, they both are great questions. The first one is actually an interesting observation. So Owlet is slightly better than the 9 microphone array. And the reason behind this is that uh, for Owlet, we use a wideband signal. We use something which sounds more like white noise, and the incoming signals has all the frequency components. And even though some frequencies are noisy, because the other frequencies have good enough SNR, the overall accuracy is maintained. But in this normal microphone array system, the way the music algorithm inherently behaves is that it only looks for certain frequencies and looks for the phase difference in that single frequency. So if that frequency undergoes noise, the entire angle of arrival is affected. So either we exactly know that which frequencies to look to, we did not discriminate over there. We evaluate owlet and the array in exact same conditions. So the same signal is going through and we are evaluating it on that. If we evaluate the arrays only on a targeted frequency where we assume that we know the input signal, that is when the 9 microphone array might surpass owlet. So this is like some unintentional resilience feature that somehow was captured in owlet just because of the wideband nature of sound. Yeah.
So the second question was basically, do you think that adding passive structures to a microphone array would make it better?
Right.
And if so, what is your speculation on how much better would that be?
Right, definitely. And I think instead of just adding the same outlet to all microphones, it will be much better if we add a different microstructure to each microphone. Because now if we know the distance between each microphone, we can emulate a much larger aperture of a structure without actually having to take that big of an aperture. So yeah, that's a great way to increase diversity. It will be very, very robust to any environmental changes.
Sounds good. Thank you. Are there any other questions people want to ask? Let's give them a couple of seconds to think about. So yeah, the talk was amazing. Thank you so much for the talk.
Thanks a lot for inviting me.
Yeah.
Always a pleasure to meet you.
Yeah. Cool. I think there are no more questions. So let's wrap up. Let's thank our speaker. So thank you, Nakul. See you.
All right. Thanks a lot. Bye, everyone.